A very warm welcome to Bite-Sized Corrosion. Let's continue with our discussion today when we're talking about what's out on site, but hopefully you will now know should not be out of mind as we look at some aspects of cathodic protection. Now, throughout this series for the past few weeks, we've been looking at what the data is that we gather, where we gather it from, be it our structure, be it our transformer rectifier, and how to interpret it and understand it. So we know we measure potentials on our pipe, we measure current and voltage output at our rectifier, and possibly we can measure the current from our anodes. And today we're going to start to explore the actions we should be taking once we've analyzed that data that we've already acquired, and what are the consequences of the actions that we're taking. So as always, I'm delighted to welcome Neil back to the microphone. And he asked us to designate the title for today's session as Turning Up the Wick. So Neil, give us the history lesson why you want that title.
Yeah, so the term turning up the wick dates back to the days of oil lamps, paraffin lamps. As you can see, I've got a paraffin lamp here in front of me, and I can adjust the intensity of the flame, or in other words, the light, by actually literally pushing the wick further up out of its housing, and we get more material burning, we get more light output. And in a way that you can equate that to increasing the output of a rectifier. We're putting in more energy, we're getting more cathodic protection. Just like if we increase the energy into the lamp, we get more light. However, we need to be a little bit circumspect about that, apart from the fact that I don't want to burn my fingers. So I want to illustrate what can happen if we turn up the wick too far. So as you turn it up, we get more light, but then it goes beyond that to a point where we've got an uncontrollable flame and lots of black smoke. Now, for those of you who didn't know anything about electricity and electrical appliances, you should by now know that all electrical appliances work on smoke. And the reason why we say that is because if you see the smoke coming out of an electrical appliance, it has failed. So there you go. Never mind the electrons we were talking about last week, it's all about smoke.
And Neil asked me to make sure that during this series, we were not telling everyone that cathodic protection is smoke and mirrors. And he just seems to have thrown that little concept out the window. I jest. Neil, let's get back to looking at, you've talked about turning up a rectifier, or turning up the wick. And in session 3, we spoke about the fact that over time, our coatings deteriorate. And so I'm assuming that we can now just turn our transformer rectifier up to give us more current to accommodate that deterioration in coating.
Yes, well, when you design a cathodic protection system, you don't design it for day one. You design it for end of life. And that end of life might be 20 years, but the pipelines that we installed 20 years ago, I can remember like yesterday. No, the current situation is that the infrastructure owners, the big infrastructure owners are saying, no, we need to design our systems for 50 and maybe even 100 years of operation. Now, you can't design a system for 100 years. Nobody's going to be around in 100 years' time that's presently alive. So you don't know what's happened. Also, we don't have 100 years of case history. We can only extrapolate. But what we do know is the behavior of coatings over a long period of time. A lot of the pipelines that we deal with have been laid coming up to 100 years ago, and we know what their characteristics are. We know that there were fuel pipelines installed between Durban and Johannesburg in the 1960s and 70s. And in the last 10 years or so, the owners of those lines have had to do significant work to maintain the cathodic protection on those lines because of coating degradation. And we spoke last week about the importance of tracking the measurements that we take and why they are so important. So when we design a system, and this is often a criticism that is laid against CP designers, they say, why have you over-designed this system? Because let's just use a number. We put in a rectifier that is rated at 20 amps, and you energize the cathodic protection system, and it's running at 5 amps. And the immediate question is, why have you wasted my money? Why have you put in all this infrastructure when I don't need all of that current? Well, the point is, you're not designing for now. You're designing for 5, 10, 15, 20, 30, 40, 50 years' time. And this coating degradation is not linear. It starts slowly, it speeds up, and if you're lucky, it will eventually level off. The different coatings behave in different ways in that regard. So, for example, polyethylene coatings generally will tend to level off, whereas bitumen and epoxy coatings will just continue to asymptote towards bare steel, for example. So the design of the CP system then is based on maybe 30 years' time, and we know a certain amount about the characteristics of these coatings. So we'd say, okay, so the system that we've installed, we anticipate that in 15 years' time or 20 years' time, it's going to be drawing 15 amps, not 5 amps. And therefore, we have a system that is capable of handling that current when it gets there. It's never a good idea to run a system at its maximum capacity. It's a recipe for burnout. And so we start with these very, very low values, which then gradually increase over time. But you get to a point where you cannot continue turning up the wick. And that's really what we want to talk about today. We don't want that conflagration, either in reality or in the equivalent of what might go wrong on the pipeline.
So Neil, if we can't keep turning it up, as you call turning up the wick, the sort of sense is, I go into the rectifier, having looked at my data, I'm not getting enough protection, and I crank it up. And I'm obviously, or maybe not obviously, let me state, I'm talking about an old system. And then what? If I'm not getting an improvement, why not? And why? And what can I do about it, I guess, is the question.
Okay, well, let's take the first question first. Why am I not getting an improvement when I turn up the wick? Well,
yeah, that's a good question.
It's actually a fairly complex situation, but the underlying principle is that a pipeline system has an inherent characteristic that we call the characteristic resistance or characteristic impedance. And this is a function of the electrical characteristics of the coating, which is what determines how much current is needed per unit area, for example, and the electrical characteristics of the pipe, which is obvious, after all, is the conductor that we're shoving this electricity down in order to get the energy to the interface 20 kilometers down the line to provide the cathodic protection electrochemical reaction. It gets to the situation where no matter how much energy you pump into the line at the drain point, which is what we call the point where we connect the rectifier, you can't get enough out the other end to provide cathodic protection. And that is the limiting length in terms of cathodic protection. And there's nothing you can do about that in terms of your existing infrastructure. And the challenge with that is that if you do keep turning up the wick beyond the point where you can see results, you then start getting conflagration. You then start getting damage. If you think about the old-fashioned car battery, a lead-acid car battery, when you charge that battery, its voltage will increase until it's fully charged, and it will not go beyond that point. If you continue to charge that battery, you're going to boil it. All you're doing is generating heat and hydrogen. You're not getting any more charge or any more use out of that energy that you're putting in. So in a similar way with cathodic protection, you get to a point where you actually can't push any more into the existing system, and you have to do something else.
And I guess if you try to overdrive the cathodic protection system in the same way that you overcharge a battery and you cause damage to the battery, you're going to be damaging the CP hardware, the infrastructure itself, which is also perhaps an unintended consequence you don't want.
Yes, well, one of the biggest problems with that situation is that if you overdrive at the drain point and push the potentials too high, you get what we call cathodic desponding. Cathodic desponding happens in all cathodic protection installations. It's not just related to overdriving, but pipeline coatings are designed to be able to withstand the formation of hydroxides that you get at the surface, and they don't disintegrate under normal, if I can call it normal, cathodic protection parameters, say minus 850 to minus 1150 potential, those tram lines. If you exceed that, you're going beyond the production of hydroxide and you start generating hydrogen. You actually start electrolyzing water at the surface of the pipeline. Now, that's not going to give us green hydrogen that we can use as an alternative fuel. It is effectively the generation of a gas beneath the coating or at the coating steel interface, which disrupts the adhesion of the coating to the steel. Then your coating starts coming off. When the coating starts coming off, you need more current. So you apply more current and you generate more gas, and it becomes a death spiral.
If we go back to where we started in our conversation, we've got a pipeline, it's aging, our coating is deteriorating, we've seen we need more power, and we've turned up our rectifier and we're not getting it to cover our pipeline as we would like before we go and do further damage. What is a practical or realistic solution to this challenge?
There are two things that you can do. You can excavate the pipe, strip the old wrapping off it, and recoat it. And this is an exercise that is extensively done in the USA, for example, where you'll see that you have a whole train of equipment traveling down a pipeline, excavating, stripping, cleaning, and recoating. We've even seen some manual equivalent things being done in the Eastern Bloc countries where they do it manually. And you have these horrendous sort of 18th century industrial revolution photographs of people with scarves around their faces working with hot pitch and rags, recoating a pipeline. It happens. So if you reinstate the coating, you reduce the current requirement, which can then extend the effective range of the CP system. But of course, that's an expensive option. And certainly it's not as expensive as putting in a new pipeline. But of course, the other thing is you may not have the option. You may not have a license or the servitude rights to put in a new pipeline. So you may have to reinstate your existing pipeline. But the other option then is to actually put in supplementary cathodic protection systems. Because if you've got to the point where your pipeline and coating system has a limiting length of, say, 20 kilometers, and your existing rectifier spacing is 50 kilometers, then you get 20 kilometers from each rectifier. You've got 10 kilometers in the middle with inadequate protection. It won't be zero protection, but it'll be inadequate. You go to that midpoint or somewhere close and install a new rectifier. Right. By doing that, you are then providing supplementary power at that point. You're not trying to push all the current down the pipeline. So you reduce the current from the existing system, which in turn reduces the losses, as we saw in Ohm's law. You reduce the current, the voltage loss will be reduced for the same resistance. And that way you can then supplement your existing system and continue. And if you take that principle to the nth degree, you can actually cathodically protect a bare pipeline when there's no coating.
I was going to ask you about that. Can we put cathodic protection on a bare pipeline? And mathematically it's possible. Yeah. I guess it's just practically how frequently do you want to have a transformer rectifier?
Well, there was a pipeline in Namibia where they had a rectifier every 5 kilometers.
Okay, so it is doable.
Yeah, so it is doable. As long as you have
the power to run it.
Yeah, sure. That argument or that principle makes me chuckle because when you talk to the coating people, they say, oh, no, 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 the coating is the primary protection for the pipeline. And the cathodic protection is just there to back up the coating. We subscribe to that principle ourselves because we put in a lot of effort to make sure that the pipelines are correctly coated. Sure. But in that limiting situation, you can protect a pipeline with only cathodic protection, but you can't protect a pipeline with only a coating. Yeah. Because there's no such thing as a perfect coating.
I was going to say until someone designs the perfect coating, but that's a conversation for another day.
Yeah, yeah.
I want to roll us back a few steps. When we look at our data and we determine that we've got inadequate protection, the first and obvious step is to turn up the rectifier and evaluate what we see and that we are getting protection. But the cautionary to that is that if you do too much of the turning up, you may in fact be causing problems because you're not improving the protection along the length, but actually just wearing out your equipment and causing damage. Have we got that sort of right?
No, that's absolutely right. And that is where analyzing the data is so important. Because if you have a coating with a particular characteristic and you energize it, you may land up with the drain point running at maybe minus 1.6, and at the midpoint between rectifiers, it's sitting at minus 1.2, just hypothetical numbers. As the coating deteriorates over the years, and remember, this is a very slow, long drawn-out process, you will gradually find that the potential at the midpoint starts dropping, becoming less negative, even though your drain point is sitting at minus 1.6. So, okay, it gets down to 1.1, you're still happy, starts getting down to 1.0, yeah, I can live with that, starts dropping down to 950 as an on potential, and you may start to get worried. So that's fine, we turn up the wick and restore the pipeline to minus 1.2 at the midpoint. But our drain point is now running at maybe minus 2.5. And I'm talking about on potentials here. So that's including IR drops. And remember that the IR drop at a rectifier is quite high. That's the IR drop in the soil because of the proximity of the anode bed. You get to the situation where the midpoint has dropped to the lowest level that you as an operator are comfortable with. Let's call it 1 volt. And now, when you turn up the rectifier, the potential at the middle does not change. That's when you need to start considering supplementary cathodic protection at the midpoint.
I think that's
and
very
that's
helpful.
why your data recording and your data analysis is so important.
I think we can't lose sight of that, and we've said it before and we'll say it again. Keeping the data and analyzing the data and making sense of the data is really what's going to help us to make sure that our system is operating optimally, whatever its age, and then drawing the correct conclusions. And what about the comment that is, well, you know, you designed the system and now we need to put in a new rectifier? Well, that was a flawed design. Does that have any weight?
It depends on the time period. If you're 30 years down the line, it's a bit unfair to say that the design was inadequate, because 30 years ago, that may have been the design requirement that is designed for 30 years.
True.
But it's also possible and quite acceptable in your design premise to state that this system has been designed for a 30-year life, after which it needs to be reevaluated and possibly additional infrastructure installed. And there are some situations like that. I was involved with the new Dubai airport, believe it or not, where the basement of that airport is located quite deep in what is called sabha. It's a salt-saturated sand. And the challenge there is that the reinforcing of the concrete substructure is going to suffer from corrosion. So what they did was they said, well, okay, we acknowledge that that will happen, and we will make provision for dealing with it, but we're not going to do anything about it now. We will monitor the condition of the structure, and as and when it starts showing any signs of distress, we have got the facilities in place to start applying supplementary protection, in this case in the form of cathodic protection.
An interesting perspective and possibly quite a wise one. Thanks, Neil. Just before we leave the topic for today, there's always the concern associated with turning up the wick and causing all the damage, but sometimes there are unintended consequences. And I think it's worth a very brief look back at discussions we've had previously on AC interference and turning up the CP too much.
For sure. There's a strong perception around that you can control AC interference and AC corrosion by applying cathodic protection. And there was a widely accepted principle for some time, except that as we researched, when I say we, I mean the corrosion industry, researched this phenomenon of AC corrosion, we discovered there's an area in a graph of AC current density versus DC current density, where if you venture into that domain, you're going to land up with catastrophic corrosion, because the cathodic protection, and it happens at high levels of cathodic protection and high levels of AC interference. And it's quite an intricate subject, and we could probably spend a whole lunchtime talking about it. But for now, I think it suffices to just say, guys, if you've got AC interference on your pipeline, even if you've got an AC mitigation system, you need to be very, very careful about turning up the wick of the CP system.
Well, let's take that cautionary to heart and say thank you, Neil. Thank you for this fascinating discussion. And I hope that our audience has found it as interesting as I have.
Cathodic protection is one of the very few practical ways of controlling bacterial corrosion, especially on pipelines. And it's not all wine and roses, as Dr. Riza will show us, but it is something that we really need to be aware of and be prepared on how to handle it. And just in terms of turning up the wick, remember, if you've got a CP system that was designed without SRB in mind, and you find that you've got an SRB problem, you might not be able to just turn up the wick to control it.